Hello everyone and welcome to FatalSec. In this video, I am going to show you how to get a real-time trace of all the instructions which are being executed by an application using Frida Stalker. I will also demonstrate how to read the register values present during the execution of each instruction. Given that SVC instructions are often our primary targets, we will focus on filtering these instructions from the overall trace, and this will allow us to concentrate on the most relevant data or instructions for our analysis. For this demonstration, I will be using a sample Android application called Frida. I have explained its functionality in one of my previous videos, so feel free to watch that first if you are interested. For the sake of this video, let me quickly walk you through this application. It's already installed on my device, as you can see, and upon launching it, we can observe that it has three types of detections. So basically it is checking whether Frida is present on the device or if the application is being hooked using Frida. As of now, the first two detections are successful, which means that they are not being detected, and the third detection is being detected currently, and that's because the Frida server on my device is currently running. So as usual, our first step is to extract this application using APK tool. So coming to the terminal over here, you can see that I have already copied this APK file in my trainings directory. So let's quickly extract this APK using APK tool D for decompilation, followed by the file name, which is adv_frida.apk. Alright, so the application is now extracted, as you can see over here. Let's leave it here for now and let's open this APK using JetX tool. Open file, adv_frida.apk, click on open. So over here on the left pane, we have this source code, and if we expand it, we can see all the packages present inside this application. And you see that most of the package names are obfuscated and renamed to some random alphanumeric characters, right? Then if we expand the resources section, we can see that we have the Android manifest file, which is the main entry point of any application. So let's examine this first. Over here, we can immediately observe that nothing much is there, only one activity is defined, and it's having this main and launcher intent filter, which means that this activity is going to be executed first when we launch the application. So if we double click on it, it will directly take us to this main activity decompiled code, as you can see. And over here, interesting, so if you see JetX throwing this error saying that it's unable to decompile because CFG modification limit reached, which suggests that this class is obfuscated, which is not allowing JetX to decompile it properly. And in the onCreate method also, you can see that nothing is decompiled, right? But still, let's try to examine what we can. So firstly, there is this static block, right? And if you know how Java programming language works, this static block is something which is going to be executed first when this class gets loaded, right? So inside this static block, even though it's not decompiled properly, but still we can see what's going on over here. So obviously these are some mathematical and XOR kind of operations, which most likely added over here by the obfuscator. Then over here we have this system.load library, wherein this r0 variable is being passed, and this r0 variable is initialized with anti-Frida. So this must be the library name which is being loaded by this application, right? And also, if we scroll down a bit, we can see that there are these three native functions: detect Frida 1, detect Frida 3, and detect Frida 2. And in our application as well, we saw that we have three Frida detections, right? So these are the native functions which are responsible for detecting whether Frida is there on the device or not. Now, because these are native function, we have to analyze this native library to figure out what's going on inside these functions. So in an APK file, any native library which is being used by the application is present inside this lib directory over here under resources. If you expand this lib directory, you will see the architecture specific directory ARM64, and if you expand this, we have our lib antifrida.so, right? So I bet you know our next move. That's right, we are going to dissect this library using a disassembler. This time I will be using Ghidra. I chose it because in my recent polls, most people expressed a preference for Ghidra as their go-to disassembler. So let's dive in with Ghidra this time around. So in this Ghidra window, in the files menu, let's import our anti-Frida library, which is there under my documents, training, Frida Stalker. And over here we have extracted this APK file using APK tool initially, right? So let's go inside this under the lib folder. We have ARM64, and over here we have libantifrida.so. Let's open it. It automatically detected the language or the architecture of the library, which is ARC64. Click OK. OK, and now if we double click on it, it will start the analysis. Yes, and hit analyze. So because the library is pretty small, the analysis was done quickly, and there we have the disassembled code of this library. So on the left hand side under the symbol tree window, we have this exports section, and if we expand it, it will show us all the exported functions which are present in this native library. So if we scroll down, we can see our JNI functions: detect Frida 1, detect Frida 3, and detect Frida 2, right? So as of now, we don't know the logic how the application is actually detecting Frida, and we are currently targeting the SVC instructions. So let's search those instructions directly by clicking on this search menu, program text, and we are looking for SVC instructions. So you just need to put in the mnemonic of the instruction, which is SVC. Select all fields because we want to search in all the sections of the ELF binary. Over here under memory blocks, select all blocks and click on this search all button. So the search results came out pretty quick. As we can see, there are a couple of SVC instructions which are present in this native library, and most of them are coming from detect Frida 3 function, right? While the rest are invoked by this U and I functions. So let's see exactly from where this U function or I function is getting called. So if we click on the U function and look into the disassembly of it, which is present over here, we can find couple of cross references to this function, right? Also, what you can do to figure out the cross references from where this function is being called is if you right click on it and go to references and click on this show call trees, it will show you the incoming and outgoing calls. So we are interested in the incoming calls, and under this we can see that this U function is actually getting called from detect Frida 3 function, right? Similarly, let's observe from where this I function is getting called. So this I function, the disassembly of the I function is present over here, and if we follow the same exercise, right clicking on this I function, go to references, click on show call trees, we can see that this I section is being called from detect Frida 1. Alright, so we have identified two exported functions. One is detect Frida 1 and other is detect Frida 3, from where our SVC instructions are getting called, right? So what we are going to do now is we will attach our hook to these two functions, detect Frida 1 and detect Frida 3, and once a hook is triggered, we will use Frida's Stalker API to trace all the instructions these functions execute. This approach will provide us with a comprehensive trace of these functions. So without further ado, let's switch to VS Code and begin crafting our Frida script. Let's create a new file called script.js. Now, in order to hook these functions, detect Frida 1 and detect Frida 3, we first have to figure out the base address of this native library, which will tell us where this library is loaded by the application into the memory. Okay, so firstly, as we know that Android DL open function is the function which gets called internally by the operating system whenever an application wants to load a new native library, right? So let's first hook this function and look for our target native library, which is libantifrida.so. So for hooking, we are going to use interceptor.attach API of Frida, and this API takes two arguments. First one is the target address of the function or the instruction on which we want to attach our hook. So in this case, it's Android DL open function, and since it's an exported function, what we can do is we can make use of module dot find export by name API of Frida to find out the address of this function. And this API again takes two arguments. First one is the target library name in which the function is present, and if you don't know in which library the function is present, you can pass in null. Then the name of our target function, which is Android DL open, right? So this is going to be our first argument, and then the second argument is a function body where we have to define two callbacks. First one is on enter, and this has one argument which is args, and then the second callback is on leave, which has this return value as its argument. Okay, now inside the on enter function, we have to look for our target library, which is libantifrida.so. So what I am going to do is I am going to create a variable with the name target library and put in the name of our library over here, which is libantifrida.so. Okay, along with this, I am going to define another variable which is going to be a boolean variable with the name is libloaded, and I'm going to initialize it as false. Okay, coming over here inside this on enter callback, just like normal dl open function, this android dl open function also takes library name as its first argument. So the arguments whichever are being passed to this function, we can access them through this args variable inside this on enter callback. For that, what we can do is to use memory dot read c string API, and inside this we are going to pass in args0, which is the first argument of this function. So what's happening over here is basically we are going to read the memory address which is pointed out by this args0 argument as a string, because we know the type of the argument, right? And let's store it into a variable called library path. So this will return the whole library path from where the library is going to be loaded into the memory by the application. Now, because an Android app during its life cycle calls so many native libraries during runtime, we want to make sure that our target library is loaded. So for that, we are going to make use of this if statement, and it's going to be a simple if condition where I'm going to check whether the library path which is coming over here has our target library or not. If it contains our target library, I'm going to simply put a log, and I'm going to say loading library path. Okay, after this I'm going to make this is library loaded variable true. That's because of how Android operating system handles the memory and the way it loads the library into the memory, chances are that this on enter function is going to be called multiple times. Okay, so we don't want to repeat the same exercise again and again whenever the library is getting loaded. That's why we have created this variable. And now inside the on leave method, so at this time inside the on enter, our target library is being loaded into the memory. It's not fully loaded, so we have to wait for this function to finish, and for that we have this on leave method. This will be called once this Android DL open function finish its execution and it's about to return. So inside this on leave, we will check if our target library is loaded or not. If it is loaded, then what we are going to do, we are going to store our target library or module into this variable using process dot get module by name API, and this takes the name of the library which we have defined at the top, which is target library, right? So basically now inside this target module variable, we have access to libantifrida native library, and let's put a log as well which says that our target module is loaded at, and now we are going to print the base address where the library is loaded in memory. For that, we can use this target module variable and access its base address using dot base attribute. Okay, I think it's time now to save this script and let's try whether it's working properly or not. So let's go back to our terminal, clear this out and over here we have our script.js file. Before executing, what I generally do is to create a new virtual environment using python 3-m virtual environment, enter. Alright, so now we have this virtual environment created. Let's activate it using source virtual environment bin activate, and let's install Frida tools quickly. Okay, done. Now let's give this script a try. Now in order to execute the Frida script, we have Frida -u followed by -l script.js -f to forcefully spawn a new instance of our target application, followed by the application name. So from the JDX GUI, if we go into Android manifest, over here we have the package name. So let's copy this and go back to the terminal and paste it, enter. As you see, the application started, and this time all the detections are triggered, and in the logs we can see that our target library is loaded at this base address. And you all can observe that it's being loaded multiple times. And also, instead of the name of our target library, we are getting this object. So let's fix this by going back to VS Code. So firstly, this object is coming because we have printed the whole target module, which is an object. What we have to print is the name of the target module. So for that, what we can do is, just like this base attribute, we can use name attribute. Okay, now let's fix the second issue. So over here we have this is library loaded variable flag. What we forgot to do is to set it as false. So let's test this out now. Going back to our terminal, exit this instance, clear, launching the Frida script again, enter. And this time you can see that we are only getting this log one time, and also instead of the object we are getting the name of our target library, which is libantifrida.so. Great. So once the target module is loaded, what we can do is to attach the hooks on the two functions which we have identified in Ghidra. First one is this detect Frida 3 and other one is this detect Frida 1, right? So heading back to our script, inside the onLeave callback, we are going to again make use of this interceptor.attach API, and this time we want to attach our first hook for detect Frida 1, which is present at this offset. Now, okay, before moving forward, one thing we have to fix is the image base address which is assigned by Ghidra. So you see currently the offset shown by Ghidra is 10176C. This is not the real offset. To fix this, what we have to do is we have to click on this display memory map icon, then go to this home icon which says set image base. Click on it, and over here you can see that the image base address is this. Let's make it 0. Okay, it will take some time for relocation fix up, and once done we will get the correct offsets. So coming back to detect Frida 1 function, it's located at this offset. Let's copy it, and in our interceptor.attach API, the first argument, as I have already explained, is the target address on which we want to attach the hook. So in this case it's this offset, right? But wait, this is the offset, not the real address in the memory. So to get the real address, what we have to do is we have to add this offset to the base address of our target module. So we already have our target module inside this target module variable. Then using the base attribute, we can get the base address of our target module. Then we can simply add the offset which we have identified like this. Then the second argument is the function body, which again takes two callbacks on enter and on leave. Right, for now I am just going to put a log which says entering detect Frida 1. Okay, because we know this offset is associated to detect Frida 1 function. Similarly, in the on leave callback, we can put this log leaving detect Frida 1. So just like this, we can create another hook for detect Frida 3. Right now we have to replace this offset with the offset where detect Frida 3 function is present. So going back to Ghidra, and here we have our detect Frida 3 function, and going to detect Frida 3 function, it's present at this offset 183C. Let's copy this value and put it over here instead. Okay, also before moving forward, what I would like to do is to store these hooks into a variable which we are going to use later on with our stalker code. So for that I am going to create two new variables. One is where hook 1 and other one is where hook 2. Okay, so I'm going to assign the first hook to the first hook 1 variable and the second hook to hook 2 variable. Okay, let's save the script and let's try to run it once and see how it goes. Going back to the terminal, closing this instance and running the Frida script again, hit enter. Cool, so application is launched, and in the log we got our desired output, which is firstly our target library is loaded at this base address, then exported function hook is triggered. First one is detect Frida 1 and then the second detect Frida 3. Looks good so far. let's get back to the script and write the code to trace all the instructions which are being executed by these functions. So what I'm going to do is to create a kind of a utility function with the name start stalker. Okay. Now inside this function, I'm going to call Frida Stalker API, which is stalker.follow. This API takes two arguments. The first one is the thread ID, which identifies the current thread which is executing this program. And the second is a function body where we define a transformation callback. So let's put thread ID as the first argument, and because it's a utility function, we have to take this thread ID as the argument from where we are going to call this start stalker function. Now for the second argument, we are going to create a function body inside which we have to define our transformation callback, and this transformation callback has one argument to offer, which is iterator. This iterator gives us access to each instruction which is being executed by this thread. Okay, so let's define the body of this transformation callback now. Inside this, firstly, because we have an iterator which contains instructions as they are being executed, so what we can do is to iterate over each instruction one by one, and for that I am going to use a while loop. Okay, and this loop is going to run until this iterator becomes null. So how I can do this is, let me create a variable called instruction. Okay, and now what I am going to do is to initialize this instruction over here and making use of iterator.next function. So this next function will give us the next instruction. It's just like how we do I++ in a normal for loop. Okay, and we have to run this until it becomes null, which means that now there are no more instructions left to execute. Now inside this while loop, we can access each instruction directly using this instruction variable. So to print it as a log, this instruction is an object, so we have to convert it into a string format using instruction.toString method. Okay, let's save it as instruction string. All right, now this instruction string variable contains the instruction which is being executed currently by the application. However, before printing it, let's also determine the instructions offset. This will allow us to map it to the disassembled instructions which we have in Ghidra. So to calculate the offset, we will use this instruction object again, but we want the offset. In any disassembler, you will see the offsets rather than the absolute address. So to calculate the offset, we will use this instruction object, and this instruction object has address as its attribute, which gives us the absolute address of the instruction present in the memory. So let's store that in this offset variable instruction.address. Okay, however, in any disassembler, you will see the offsets rather than the absolute address, right? So we have to subtract the base address of our target module from this absolute address, which will give us the offset of the instruction. Currently we don't have that target module base address in this start stalker function, right? So let's take it as another argument, and now what we can do is to simply subtract this target module base address from the absolute address. Okay, let's print these information in a log. Let's print it using this console.log API. So firstly, I'm going to print the offset followed by the instruction itself. Okay, however, there is a small issue. This will trace all the instructions, including those which are not part of our target library. For instance, if our target library, which is libantifrida.so, makes an external function call like open from libc library, Stalker will trace those instructions as well. Once the Stalker API starts tracing, it doesn't distinguish between instructions from the target library and others. As a result, we will get hell lot of output which we even don't want. So to address this issue, we can use an if condition to check whether each instruction's address falls within our target's library range. So let's quickly do that. Inside this while loop, we can make this if condition where the instruction address is less than equal to our target module dot base address dot add. So here I'm going to compare it with the upper limit of our target library. Calculate the upper limit. I'm going to add the size of our target library with its base address. Okay, which we can calculate using this size attribute. And instruction dot address is greater than or equal to target module dot base. Okay, let's move these statements inside this if block. I hope it's clear. What I have done over here is just put an upper and lower limit. If the instruction address which is being traced by the stalker is greater than our target module's base address and less than the size of our target module, then only we will log it. Otherwise, we will not log it. This way we can make sure that all the instructions which we see in the log are from our target library itself. Okay, I think our stalker function is ready now. Let's call it inside the hooks which we have defined over here. Remember, we want to start tracing the instruction as soon as these function gets triggered, right? So inside on enter, I am going to call this start stalker function, and we have to pass two arguments. First one is the thread ID, which we can get easily using this dot thread ID. Then the target module, we already have it over here, right? Similarly, let's call it inside this hook as well. Okay, wait, are we really done now? Not quite yet. There's still a crucial step we are missing. Can you guess what it might be? Think about it. So we have started stalking our instructions, but we haven't considered when to stop it. And that's a pretty important detail, isn't it? For that, let's create another utility function and let's name it as stop stalker. Okay. Inside this function, I'm going to call stalker.unfollow API, which will tell the stalker to stop tracing the current thread. And this actually takes one argument, which is the thread ID. Again, in this utility function, we don't have the thread ID, so we have to take it as an argument. Okay. And if there are multiple instances of stalker running, we can stop those as well using stalker.flush. Let's call this utility function inside onLive, because that's when we want the stalker to stop tracing the instructions. So we have to pass thread ID. Let's copy and paste it over here as well. One more thing we have to consider is to detach the hooks which we have defined. This is not mandatory to do, but it's a good practice to do it, because in case your exported functions are getting called multiple times, then that will cause this stalker function to be called multiple times, which will create a lot of overhead and it might cause application to crash. So that's why we have stored our hooks in this hook variable. So now we can make use of this hook variable to detach the hook. Similarly, for this as well, we can make use of hook2 variable to detach it. Alright, I think we are pretty much done now. Let's save the script and spin it up for testing. So going back terminal, closing this instance and launching the script again. What do we get? Type error, not a function, start stalker at 59. Okay, small typo guys, so this has to be stalker.follow. Okay, launching again and the application crashed. Okay, this is not what we have expected. Let's see if we have missed anything in our script. Okay, our target library, it's defined. Inside onLive we have our hooks. These offsets are correct. Start stalker, stop, detach. Okay, this looks good. Inside the start stalker function, we have stalker.follow. While loop, iterator.next is going to iterate over the instructions one by one. Then we have a if condition, and okay, yeah, we have missed one important point. We have to call this keep function. So this will tell Frida to keep tracing the instructions after the current instruction gets executed. So that's what we have missed, and hopefully everything should be good now. Let's head back to the terminal, clear it out and launch the script again. So the application is launched, and in the logs you can see that we are getting all the instructions detect Frida 1 and the instruction which are being executed, then detect Frida 3 and the instructions which are being executed, right? So now we are able to get a trace of all the instructions, and in between these traces, if you observe closely, you will be able to see the SVC instructions which we are looking for. In this application, the code is not very big, So we can kind of observe these SVC calls manually by looking at this trace. But what if we get a huge trace with millions of instructions? Then how will you filter out these SVC instructions? Don't worry, we can only get a trace for certain instructions instead of all the instructions. For example, here our target is to trace the SVC instruction only, right? So if we go back to our script, we can simply put a if condition right before our log, and using this instruction object again, by making use of mnemonic attribute, we can compare the instruction, and if it is SVC, then only we are going to print the log. Okay, so it's as simple as that. Let's save the script, head back to the terminal and launch the script again, and this time you can see that we are only getting the trace for SVC instructions. However, just by looking at this trace, we cannot tell what this SVC instruction is doing, right? So what's next? During an assignment or a pen test, we need to figure out exactly what these SVC instructions are doing. And the good thing about Stalker is that it gives us access to almost everything, such as registers. So using the registers, we can actually print what's going on with these SVC instructions. So we have already seen many times in our previous videos how to parse a SVC instruction manually. Let's do it one more time so that you know which registers are involved during the SVC instruction. If you go to this website, link of which I will put in the description box, okay, you can see that we have this Linux system called table, and over here under the content section you can see different architectures. So if you are dealing with, let's say, ARM architecture, then you can look for ARM specific system call table. Currently we are dealing with ARM64, so let's go to that system call table. So as you can see over here in the fourth column, we have these SVC number or system call number in hex form. So basically each function is mapped to a specific system call number. For example, here this setX attribute function is mapped with hex 5 system call number. So whenever we pass hex 5 in SVC instruction, it will call setX attribute function, okay? And if you look at the heading of this system call number, it says x8, which means that this system call number is going to be stored in x8 register, okay? So if you want to know which function SVC instruction is calling, we can look at the value present in this x8 register. Similarly, other columns will tell you the different arguments these functions take. So again, if we look for setX attribute, the first argument this function take is path, which is stored into x0 register. Then its second argument, which is name, is stored into x1 register, and so on. Okay, now let's head over to the script and let's only print the system call number. But there is a small catch. Like I said, Frida Stalker provides access to all the registers, but we cannot access them directly over here. For that, we have to make use of another API, or you can say a callback. It's not exactly a callback, it's a call out. So because we are only targeting the SVC instructions, let's leave this if statement as it is. And inside it, we are going to make use of another function which is provided by iterator, which is put call out. Okay. This function sets a callout that will be invoked by Stalker during the tracing of the target process, which means that it will not block the current running thread, and we can do any type of heavy work in this callout function. Also, from the device point of view, printing the logs onto the console is also considered as a heavy operation. Okay, so it's always a good practice to print the logs in this put callout function. Okay, so this put callout function basically has one function which provides us with this context. Okay, and inside this function we can put our log. Now inside this put callout, we don't have access to offset and instruction str variables. Also, we don't have access to this instruction variable. So what we have to do is, let's move these instructions inside put callout. Okay, and now what we have to do is to figure out the instruction which is being executed. So this context actually contains all the required information about the registers, the instruction which is being executed, and everything. So as you know, in ARM64 architecture, we have PC register, which stands for program counter, which contains the address of the instruction which is being executed currently, right? We can use instruction.parse API of Frida and over here we have to pass the PC register, which we can access using context.pc. Okay, so now this PC will give us the address of the instruction which is being currently executed, and using this instruction.parse API we can get the instruction object. So now we have our instruction variable inside this as well. Let's save the script and run it one more time to see what do we get. All right, looks like we are getting quite a lot of SVC instructions this time, and now the trace is completed. As you can see, we got hell lot of instructions this time as compared to the previous output, and that's because printing the log in the console is an expensive operation and it does require significant amount of time to print it, because of which when we were printing it directly we were not able to capture all the logs, right? Let's go back to the script, and just like we access the PC register, we can access all other registers. So we just saw that the system call number is stored in x8 register, right? So let's access it using context.x8, and I'm going to store this value into x8 variable. So this is a variable, not a register. Register is this one, and I'm just going to store it into this variable. What I want to do now is I am going to print this system call number in our log. That way we will know which function SVC instruction is calling. That's it. Clearing this one out and launching the script again. And now you can see in our output trace, we are able to get the system call number as well. And we can see that the last SVC instruction called this system call number, which is hex 39. Let's see what this system call number is associated with. So if we go back to this table and look into this fourth column, hex 39, which is over here, this is associated with close function. Okay, so this means that this SVC instruction which is present at this offset is actually calling the close function. Let's also see what hex 3f system call number is mapped with. Hex 3f is over here and it's mapped to read function, which means that this particular SVC instruction at this offset is actually calling read function. Similarly, you can identify rest of the SVC numbers. So far we have identified that it's calling close function, then read function. Let's also see what 3e means. So 3e is right above this and it's mapped to lseek. Okay, then again 3f, which is read, then we have 3e, which is lseek, then read all the way up to here, then again lseek, then read, then we have hex 38. Hex 38 is for open at function. Okay, which means it's actually opening a new file over here. Makes sense? So if you observe these particular set of instructions, you can tell that the application is actually opening a file, then it's reading it, then it's calling lseek function to move file descriptor to a specific location inside the open file, and then it's reading it from there. Then again it's calling lseek function to move the file descriptor to a specific address inside the file, and then again it's reading, and then finally it's closing the open file, right? So that's how you can observe the SVC instructions and what they are doing. But that's not it. Let's go one step further. So going back to the script. So now we know what all function these SVC instructions are calling. What we can do is we can simply make use of switch statement and look for the functions which these SVC instructions are calling, and then we can print out the arguments, right? So you can either use if else statements multiple times, but for simplicity and for code readability purpose, I'm going to use switch statement, and I'm going to compare the system call number which is there in this x8 variable with the one we have identified in the log. So the first one is close. So currently the x8 variable is containing a hex value, and it's not straightforward to compare two hex values directly. So what we can do is we can convert this hex value to integer like this, and then we can compare the integer equivalent value. So for instance, for close function, so its integer equivalent is 57. So we can do like this, and let's move this log inside this, and now we know which function this 57 belongs to. So let's simply print it. before moving forward, let's quickly do a check whether it's printing it correctly or not. Okay, cool. So we are able to get the trace along with the system call number and the function to which it is associated with. Let's do the same for rest of the system call numbers. The other one which we have observed was openet, which is hex 38 and its integer equivalent is 56. So case 56, copy this log and paste it over here, and this belongs to openet. Now we also want to print the argument which will tell us which file this openet function is calling. For that we can come back to this table and look for its argument. So the first argument is a file descriptor and the second argument is the file name. And if we look at this column's heading, it's pointing to x1, which means x1 register is containing the file name of this function. So you know how to access the register now. And the file name is of type character pointer, which is nothing but a string. So we can use memory dot read c string API of Frida, and our argument is there in x1 register, right? Save it. Let's see what do we get now. Exit, clearing out the terminal and launching the script again. Cool. So this time you can see that this svc instruction which is present at this offset is making a call to this system call number which is associated to openet function, and this openet function is actually trying to open proc_self maps file, and then it's closing this file. In between we have not traced, then it's opening another file which is libc.so, and then it's closing it, right? So that's how you can get a nice trace of all the svc instructions, right? So that was it. I hope this information is useful and you learned how to use Frida Stalker API and how to trace the instructions, how to pass the arguments, how to access the register values, right? Thank you so much for sticking around and see you soon in another video.